Hi everyone, welcome to this short video. I'm going to try my best to keep it short on ECG basics. You guys requested for something to help you get through the ECG, and you've got some incredibly detailed notes from clinical skills that actually tell you everything you need to know about the ECG, but I can understand that it can be really overwhelming when that's the first thing you read. So what I'm aiming to do with this is to give you a very simple, very basic core of the principles of ECG, but this is not the level of detail you really need. So once you get this, it should be a lot easier to plug in the details from all the other sessions that you've had, but I hope this just helps you to make sense of things. So just to recap, you know this is the heart, and the heart consists of cardiomyocytes. And if you get really close into those cardiomyocytes, you can see the individual cardiac muscle cells. Now, at the level of each cardiac muscle cell, the cell membrane contains different ion channels that allow the movement of different ions that is responsible for generating the action potential that you would record from a single cardiomyocyte during a depolarization, which then results in the contraction of the cardiac muscle. And what you see on the ECG is the composite of all those action potentials across the entire heart, and that net depolarization is what you see as the ECG. And it is also important to realize that because this depolarization is taking place in the individual cardiomyocytes, the net direction of depolarization would go in the direction where there is the biggest muscle bulk. And the chamber of your heart with the biggest muscle bulk is your left ventricle. So the direction of net depolarization of the heart would be from the SA node, which is your usual pacemaker of the heart, down towards the left ventricle. So it will go in this direction. And later on, you're going to see that because it goes in this direction, the leads that face in this direction will be the ones with the greatest net positive depolarization. Okay, this picture is meant to show you the positioning of the leads that you would put on a patient when you want to do an ECG. So you can see there is one lead on each of the four limbs, and those limb leads will be calculated by your ECG machine to give a net depolarization in these directions for leads 1, 2, 3, AVF, AVR, and AVL. And then you have the chest leads, V1 to V6, which are positioned like this with orientation to the heart. And that would then give you the horizontal sort of cross-section showing you the depolarization of the heart in that direction. So another key concept you want to keep in mind when you're actually interpreting an ECG is to be aware of how those different leads that you have placed on the patient will record a wave of depolarization with respect to the direction that wave is moving. So if you actually have a lead here, this is your ECG lead. If you have a wave of depolarization that moves away from the lead, when you record that tracing on your ECG paper, it will show a downward deflection. But if you have a lead that's sitting in the middle of a muscle fiber, when the depolarization wave is moving towards that lead, you will see an upward deflection. So if you were to imagine that this wave of depolarization moves towards the muscle and then it bypasses the muscle and goes past it, it will go up and then down. So that's how the waves of depolarization on your ECG paper get created. And if you imagine this is your heart and your net wave of depolarization is moving that way from SA node towards the left ventricle, you can see how those waves of depolarization would happen. So with respect to this lead, you would see it go up, and then as it passes, it will come down. But if it's the lead right here in the middle, it actually goes past it and then moves away from it. However, with AVR, it's moving away from it all the time. And that is why with the different leads, you actually have a different appearance of the ECG wave at normal baseline. Okay, so just a quick recap of what you actually see in your ECG tracing and how you figure out the voltage that is represented and the time scale that is represented. You have to always start by calibrating your ECG machine so that at a baseline you know that a voltage of 1 millivolt will record as 10 millimeters. That then allows you to calculate the degree of the voltage that is being measured based on the degree of deflection that you're going to see on your ECG tracing. And the time scale that you're going to see is because your ECG paper moves at a fixed rate. So you know that one large block of 5 millimeters represents 0.2 seconds or 200 milliseconds. And if you have one small square, that is 40 milliseconds. So knowing that time allows you to calculate the time that's actually represented by the different segments on your ECG, which would then represent the time it's taking for the wave of depolarization to move through your heart muscle. Okay, so this is the ECG wave that you should be pretty familiar with by now, but just to recap, you start off with the isoelectric line before any depolarization takes place. Right here is where your SA node depolarizes, and then as that spreads over your atrial muscle, you get your P wave, and so that's your P wave. And then you have that depolarization going to spread down to the ventricle. So in that point, while it's spreading down via your AV node, you have your PR segment. And from the start of P wave until the end of the PR segment, which is where your QRS complex begins, that's your PR interval. Then you have your QRS complex, which represents ventricular depolarization. The first downward deflection is called a Q wave, and the first upward deflection is called an R wave, and a downward deflection after the R wave is called the S wave. Not every wave is going to have a Q, an R, and an S, but by default we call the whole complex a QRS complex, even if it doesn't have all three components. And then from here you have the ST segment, which is from the S wave to the start of the T wave, and that's usually isoelectric. And then you have the T wave, which represents ventricular repolarization. And the two main intervals you talk about in the ECG are the PR interval and the QT interval. And they have different significance, which you will see in your more detailed notes. Okay, so we've kind of touched on the origin of the segments of the ECG wave, but if you look at this diagram, it shows it in a little bit more detail. The numbers here correspond to the numbers indicated on this ECG wave. So you can see 1 represents atrial depolarization begins, and it actually spreads over the muscle of the atrial chambers, the right and the left. And it's spreading through the gap junctions in the cardiomyocytes via the intercalated discs, so it's a smooth spread. And you can see that happening, so that's the wave you're going to see from atrial depolarization. And then at 2, the atrial depolarization is complete, and the electrical impulse cannot spread directly down to the ventricles because there's a fibrous skeleton in between the atria and the ventricles. So it can only pass through the conducting pathway, which is via the AV node. So there's a pause there because the AV node conduction is slow, and that is to give the atria time to actually contract and fill the ventricles, and only when the ventricles are filled will they contract. So then the wave of depolarization spreads down the Purkinje fibers and down the right and left bundle branches to depolarize the ventricular wall, and that's where you get your QRS complex. So number 3, and then you come to number 4. The ventricular depolarization is complete, so there's an isoelectric period, and repolarization begins, which is what you see as your T wave, and then you have a period of rest before the next contraction begins. So you can see here that actually the interval between the two R waves actually represents the time between one entire cardiac cycle. You could look at the start of the P wave to the P wave, but it's easier to see that exact pinpoint distance from R to R. Okay guys, so we know that the distance between two consecutive R waves represents the distance between one heartbeat and the next. And we also know that the speed the ECG paper moves through the machine is 300 big squares per minute, because that's how it's calibrated. So if you take 300 and divide that by the number of big squares in between two R waves, that will give you the number of heartbeats in 1 minute. So in this diagram, you can see there's 5 big squares between the RR complexes. So if you take 300 divided by 5, you find the heart rate, which is 60 beats per minute, which is just on the border of low heart rate. Normal heart rate is between 60 to 100. So by calculating the heart rate by this method, provided the rhythm is regular, then you can figure out the heart rate, and you can decide whether this patient is bradycardic or tachycardic or has a normal heart rate. Deciding whether this heart rhythm is coming from above the ventricle or below the ventricle, supraventricular or ventricular, you need to look at the conformation of the QRS complex, and we'll talk about that a little bit when we get to the next portion. Okay, so now this is a little bit more about looking at the direction of depolarization of the heart muscle in a little bit more detail to help you figure out why the QRS complex has the morphology it does in the individual chest leads. So what happens is your depolarization actually starts from the SA node. And from the SA node, it's going to depolarize the atria. From the atria, it's going to come down the AB node and it's going to depolarize the septum from left to right. And then it's going to move through the left and right bundle branches respectively. But because the left ventricle has a much bigger muscle mass relative to the right, the net direction of depolarization at that phase is very much to the left. So that's the bit represented by green in 3. And there is also, the wave is going to move up the left ventricle and you will see a net direction moving towards 4. So the waves here are going to look at V1 and V5. So V1 looks more at electricity moving towards the right ventricle, and over V5 it looks at the direction moving towards the left ventricle. And the different portions of the wave are colored based on these different arrows. So with V1 you can see as the lead moves from the SA node downwards, it's actually moving towards V1 and also towards V5. So there is this net depolarization upwards. But as it moves away from V1 and towards the left atrium, you can see there's a downward dip. Whereas over here, it's more of a smooth up and down. There's no downward dip because it's moving towards the direction of V5. And then as it moves down the atrial septum, it moves from left to right. So as it's moving from left to right, it's going to move towards V1, which is why you see an R wave first in V1. Whereas because it's moving from left to right, it's actually going to be away from V5, so you see a small Q wave first. And then the wave actually progresses to predominantly move towards the left ventricle, which is away from V1, which is why you see a deep S wave. And then it moves back towards the baseline when the depolarization is complete. However, in V5, because it's moving towards V5, you have a tall R, and then it comes down as an S and goes towards the isoelectric line. And you can imagine V2, V3, V4, which are all in between, and you can try to figure out how those conformations happen based on this movement. Okay, so let's just do a really quick review of another bit, which is the cardiac axis. And we just kind of recapped how all the different leads look at the heart from different directions, which are represented as degrees in this picture. So you can see lead 1 is actually defined as 0 degrees, all the way across here to 180, and then your AVL and AVR at the minus 30 and minus 150 respectively. As lead 2, AVF, and 3 are over here. So these are all your limb leads. We're talking about the cardiac axis, you're looking at your limb leads and not your chest leads. And your normal electrical axis sits here between minus 30 and 90. So it's over here within this green zone. If you go beyond minus 30 to minus 90, that's left axis deviation. If you go over here, between 90 to 180, it's right axis deviation. Over here, it's such extreme axis deviation, it's never going to happen, and that's called your no man's land. But I just wanted to highlight here this bit, these two red arrows between 0 and 90, which is lead 1 and AVF, give you a very good idea of when that electrical axis is actually going to be normal. Because we just saw just now that you get a net positive depolarization whenever electricity moves in that direction. So anything that moves in this direction within the normal cardiac axis would show you that this is positive. So if you move towards 1 in AVF, so you have a positive deflection 1, a positive deflection in AVF, you're almost sure that you have a normal cardiac axis. Okay, you are sure you do have a normal cardiac axis. Some people also get 1, 2 and AVF, so 1, 2 AVF all positive, you definitely have a normal electrical axis. This is just another diagram showing you another way of looking at it in case that's something you prefer. This is a table showing you how you can interpret your cardiac axis very roughly based on lead 1 and AVF, which are the two that we saw earlier at 0 and 90 degrees. So from what we saw, they're both positive, you have a normal axis. But if lead 1 is positive, lead 1 is here is positive, AVF is supposed to be here to be positive, so it's going upwards, it's negative. So you have positive, negative, then probably it's a left axis deviation. If you have a negative lead 1, meaning it's going in this direction, and a positive AVF, meaning it's going that direction, it's probably a right axis deviation. If both are negative, it's an extreme axis and it's no man's land. It doesn't happen.